Okay, this is the first of two videos for lesson 2.2, defining the derivative function using derivative notation. We're going to represent the derivative function as the limit of a difference quotient. And this is going to lead to us becoming finding functions for derivatives later on. Right now, y equals f of x, notations for the derivative. We're going to start talking about those and how we can calculate the derivative represented graphically, numerically, analytically, and verbally. So let's go and look at our lesson. We start with the limit definition of the derivative. We want to think about it as an arbitrary function. Maybe just a function f of x, doesn't matter what it is. Oops. And if you pick any value on that function and call it x, then if this function meets certain conditions, which we'll talk about later, that function has a tangent line. Well, I missed it, didn't I? A tangent line to the curve at x. That's supposed to be right here, where that line and that graph intersect in exactly one point. The line doesn't go through the point. The line doesn't go through the graph and intersect in more than one point. Just touches the graph at that one point. If the curve is sufficiently smooth for f of x, at that point, then that tangent line exists. There's one unique tangent line that does that. And so what we're going to look at is, I told you yesterday that the derivative of a function f of x, is at a point is the slope of that tangent line. So we're going to take an arbitrary x value and we're going to look at, we can calculate if we have 2 points on a curve, one where x, and then we could say this is the point where we have x equals x plus h. And we talked about yesterday how if we let that h get closer and closer to x, then that secant line, the line that intersects the curve at more than one point, becomes closer and closer and closer. As we move this x plus h closer, then these secant lines get closer and closer and closer to this tangent line. And that's what leads us to what we call a limit definition of the derivative. And the limit definition for the derivative of f of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. This is the limit definition of the derivative. Of f of x. And we're going to use that later to find functions for the derivative of functions. But for now, what I want you to understand is this limit is equal to the slope of the tangent line to f of x at x. So in order for that tangent line to exist, the slope of that tangent line to exist, then this limit has to exist, which means, as we talked about last unit, that the limit from the left has to equal the limit from the right. And what we'll see to be differentiable later on at a point, the function value has to equal that also. It's called continuity. We'll talk about that in a few days. But now let's talk about some notations for derivatives. When we talk about the derivative, if we have a function f of x, the derivative can be represented several different ways. We can say f prime of x. That's how you say that. When we talk about f prime of x, we're talking about the derivative of f of x. Or we can say the derivative of f of x with respect to x. That's what this means. This is the derivative of f of x, or f prime of x. This is the derivative of f of x with respect to x. Sometimes you'll see it just written as dy dx. Remember that f of x is also equal to y. So dy dx is also the derivative of f of x. And sometimes you might see it written simply as y prime. These are all equivalent forms, different ways to represent the derivative of f of x. And this one, we say f prime of x. That's a little f though. We'll see why it's important that we distinguish between the little f's and the big f's later on in the course. It simply means the derivative of f of x. Here, when we look at this, we're looking at, this says the derivative of f of x with respect to x. It's just the derivative of f of x. This, we say, dy dx. Again, the little letters and the capital letters make a difference. You just say dy dx. dy dx. It means derivative of y, which could be f of x, means the same thing. And down here, we often call this y prime. Oops, hold on. And I'm going to make it lowercase y. It matters. Later on, you'll see why. Y prime is just another way to say the derivative of y, which is also known as f of x. So all these mean the same thing. And we're able to find and evaluate the derivative of the point because all of these are the slopes of the tangent line, also known as the rate of change, the instantaneous rate of change at a point. So when we can find these functions for f prime of x, dy dx, y prime, they're all the same thing. If we find this function, then we can plug in an x to the function for f prime or from dy dx for the derivative, and we can find the slope of the tangent line at that point, or the instantaneous rate of change at that point. When we look at a few of the examples from your pretest, well, let's just look at this one right here. If I ask you to determine f prime at x equals 0.5, or I could say the derivative of f of x at x equals 0.5. This is the tangent line L to the curve at 0.5, and we're given 2 points on that line, so we can use those 2 points to find the slope because f prime is the slope of the tangent line. So remember, we find the slope of the tangent line, which is also equal to f prime of x, which is going to be y2 minus y1 over x2 minus x1. I get 0.5 over 0.5. That means the derivative of the tangent line at x equals 0.5 is just 1. Let's look at your pretest again. Let's see what we can do here. So here they ask you for that value f prime at 3. You're given, says this is a differentiable function, means its derivative exists, along with the tangent line of the graph at x equals 3. So this is the tangent line. So what is the value of f prime of 3? So to do that, you're going to calculate the slope of this line. I have a point here at 5, 3. I have a point here at 1, 5. Let's go ahead and do this. This is the 0.53. This is the 0.15. So f prime of 3 is the slope of the tangent line at 3, which is going to be 3 minus 5, this is a 5, over 5 minus 1. 3 minus 5 over 5 minus 1. That's equal to negative 2 over 4, or negative 1/2. When we look at that, negative 1/2 was answer right. Here's a pretest. Equation for the line tangent to the graph of a differentiable function f of x, or f at x equals 3. Okay, so this is the equation of the tangent line, y equals 4x plus 6. Which of the following statements must be true? Let's look at this one a little closer where I can draw on it. Okay, remember, this is the tangent line. The slope of the tangent line at x equals 3 is the derivative at x equals 3. So f prime of 3 is equal to the slope of the tangent line at 3. So 3 is definitely true. Now, because the graph has to intersect the tangent line at the point, this was the point 3 something, it has to satisfy the equation of both f of x. So you plug in f of 3, that has to equal the same thing you would get when you plug in 3 to the tangent line equation. So that means that f of 3 has to also equal what you get when you plug in 3 to the tangent line equation. So we're going to get 4 times 3 plus 6. Now this is the only point on the graph that's true, unless the graph intersects some other later on. But in this neighborhood, in this close proximity, this is the only place that is going to be true, that you can only plug in to find f of 3. You can use the tangent line equation, is at the point where those two graphs intersect. So here we're going to get 18. F of 3 is that's true. Now we have no idea what f of 0 is, because this function could go down like this function could go here, and this could be where x equals 0, the y-axis, and these two values could be different. So we cannot say f of 0 equals 6. So this would be 2 and 3 only would be our answer to this one. If we look at the third one on this, oops. Oh, we're given a graph. Let's go ahead and take this out. If we let f be a differentiable function with f of 1 equals 3, notice, pay special attention, we're given the graph of f prime. Part of this course, we're going to be given information about f prime and have to infer things about f. Sometimes we're going to be given things about f and have to infer things about f prime. But you need to pay special attention to the markings on the graph and see if we're given the derivative or the function itself. says let f be a differentiable function, f of 1 equals 3. The graph of f prime, the derivative of f, is shown above. Which of the following statements is true about the line tangent to the graph of f at x equals 1? Okay, all I know right now is that f prime of 1 equals 2. That right now, what we know so far, that's all I know about the graph of this function. And that means that the derivative at f of x, or derivative of f of x at x equals 1 is 2, or the slope of the tangent line at x equals 1 is 2. So the tangent line slope has 2, and it passes through the point 1, 3. Let's see, we're going to have to be able to infer something about a point. We're going to figure that out in a few moments, though. Okay, we're going to have to find the equation of the tangent line. But for now, let's leave it at that for this first part of the video.